The next chapter which we're going to deal with is theory of equations. So what is theory of equations? Now we have discussed different types of equations or the functions which we have dealt in previous sessions. So to start with, we have discussed about a linear equation which was y equal to mx plus c. Then we have also discussed about quadratic equation in the recent session of the topics, which was in the form ax squared plus bx plus c. So etc. and etc. We have different types of equations which are decided on the highest power they have. Say for example, if my linear equation is y equals mx plus c, my quadratic, which is y equals ax squared plus bx plus c, or next, if it is cubic, the next which comes in order, if it is cubic, then this is in the form ax cubed bx squared plus cx plus d. Then there is one common property which I identify in each of these, where I identify that linear, my power of the variable x is 1, and for quadratic, the power of the highest power of the variable is 2, and in cubic the highest power is 3. So each of the highest powers of x decide the different types of equations. Linear, the power is 1, quadratic, the highest power is 2, for cubic the highest power of 3. Now what happens if I have an equation where the power is n, is what we are going to discuss, and this theory of discussing each of the powers in its expressions is called theory of equations. It may be any equation whose power is n, or x power 100, x power 1000, but for any equation we just examine the properties, we examine the roots, we find various other properties. As we have found in quadratic equations, there are two roots, the roots being real and equal, real and unequal, or imaginary or complex. So these are the different properties which we have identified in the nature of roots of different equations which we have considered. Similarly, we are going to enter into the general form of x power n sort of equations, which are called the polynomials, which we are going to discuss in the next session. But the study of each of these for their roots, for their connection of the roots with coefficients and various other properties comes under theory of equations, to be continued with the session. Now let's start with the first topic of first content of this theory of equations, which starts with polynomial. Now the whole of theory of equations is based on a polynomial. So it is very important to know what is a polynomial before we understand the further properties of theory of equations. Now as we have the word polynomial, it is defined in this manner. If n is a non-negative integer and if I have a0, a1, a2, ai till an are real or complex numbers, then for a0 not equal to 0, it is defined that a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 till ai x power n minus I till an minus 1x till an is how I define the polynomial this. Then for a not equal to 0, this is called a polynomial in x. Because the variable is x, I call this as a polynomial in x of degree n, because the highest power in this case is n. Therefore, the degree of the polynomial is n. So the definition is including all the factors here, which says that if n is a non-negative integer, that is, it can be either positive or 0, is a non-negative integer, and a0, a1, a2 till ai, so on and so forth till an are real or complex numbers, then for a0 is not equal to 0, my function f of x equals a0 x power n plus a1 x power so on and so forth is called a polynomial in x of degree n. So therefore, this is how we define a polynomial in general sense. Any expression which can be written in this form and satisfying each of these properties is called a polynomial. Let's see some contents here. Here, the special property is that a0 is called each of ai, or a0, a1, a2, so on till an are called coefficients of the given polynomial. The constants a0, a1, a2 till an are called coefficients of the polynomial, and a0 is given with the special name called leading coefficient. So this has a very vital role to play, because this is where I call a0 as the leading coefficient, which is never 0. So therefore, a0 is called the leading coefficient. And finally, this is a special coefficient because every coefficient is connected with x, but this is the only coefficient which is independent of x. Therefore, my last coefficient, which is generally denoted with an or with degree n, is called the constant coefficient. Or this is called the constant term. Now, as it comes to this, my an is the constant term, and each of ai, as I see here, I see that the general coefficient ai is said to be the coefficient of x power n minus I. So ai, which is called the general coefficient, is nothing but the coefficient of x power n minus I, is how we understand each of the properties, where a0 is the leading coefficient, and the leading coefficient is also called the constant term is also called the absolute term. Absolute term. So a0 is the leading coefficient, and an is called the constant term or the absolute term, and ai is called the general coefficient of x power n minus I, as can be identified here. So this entirely makes a picture of what a polynomial is. You can take many examples out here which satisfy. For example, if I take the polynomial p of x is root 3x cubed minus 7ix plus 4, then this is clearly a polynomial of degree 3 in x, because each of the coefficients are complex, because it can be real or complex, and each of them with a0 being root 3, and my next a1 is 0 because there is no x squared term, and my a2 is negative 7i, and my a3 is 4, and therefore each of the coefficients are derived from the given polynomial. So this is a polynomial in x of degree 3, is how we understand the polynomials through the given definition. Now, there is other representation for a polynomial, because some of the mathematicians also define a polynomial with its other representation as follows. polynomial which is denoted by either p of x or f of x is also given by a naught plus a1x plus a2x square plus arx power r till a and x power n is how we define a polynomial with the coefficients coming from last to first. So it doesn't matter on which order the coefficients are written, but the definition has to be taken care of, where if I write this, then my a naught an should not be equal to 0 is how the condition comes, where in the previous case it was a naught not equal to 0, but ultimately we understand that the coefficient of x power n should not be equal to 0, and a naught, a1, a2 till an belong to real numbers or complex numbers with this are the same thing. But in this case the leading coefficient is an, because in this case I see that the leading coefficient is the one which generates from an, therefore an is the leading coefficient, and my constant term or absolute term is a naught, is how we identify through the other representation of a polynomial in this manner. So this is equally a polynomial in x of degree n. No doubt the definition is still the same, that this is a polynomial of degree n in x with its coefficients respectively being a naught, a1, a2 till an, with leading coefficient an and constant term a naught, and the general term is ar or ai is how we understand the concept. So equality of polynomials. Now what happens when the two polynomials are equal is what we are going to discuss here. So let's see the condition for equality of polynomials. So in order to do this, let me consider two basic polynomials and study their equality process. So the two general polynomials, both of degree n, I take are as follows, where I take firstly p of x, which is in the form a naught plus a1x plus a2x square till an x power n is the polynomial I take of degree n in x. Similarly, I take the other polynomial q of x, which is b naught plus b1x plus b2x square till bnx power n. Now in this case an is not equal to 0, in this case bn is not equal to 0 and are the leading coefficients respectively for px and qx, and these two are the constant terms respectively. So the two polynomials px and qx are equal if and only if I say that each of their coefficients are equal for all 1 less than or equal to k less than or equal to n, that is starting from 0 for all 0, that is when I take k is 0, 1, 2 till n, is how I understand the equality of the polynomials. So two polynomials are equal if and only if their like coefficients are equal. That is, when I take k is equal to 2, that is a2 is equal to b2, then we say the two polynomials are equal. Remember, the equality of polynomials is strictly based on equality of the respective coefficients. Very important formula out here is how we understand the equality of polynomials connected with equality of their respective coefficients. So a constant polynomial is a type of a polynomial which expects only constant, that is, it is independent of x. That is, a polynomial which has a constant term only is called a constant polynomial. say for example, I take a polynomial which is 3. Now this is strictly with a constant term. There is no x attached to it. So when you don't have any x related with the coefficient, that means that term is said to be independent of x, and hence the constant term here is this, and this is a constant polynomial. And note, the important point out here is that whenever a polynomial is constant, it doesn't have an x term. That is, I can write this in terms of x as x power 0, because this is x power 0 is 1, and I can write this 3 times 1. So when I write this as 3 times of 1, this one can be written as x power 0, which makes us understand that the power of x is 0, and hence for a constant polynomial, degree is always 0, is how we understand. Because for a constant polynomial, degree is 0, we have degree always 0 for a constant polynomial, is how we understand the degree connected with constant polynomial. Now here, one of the interesting result which comes is 0 is also a constant. So is this, the question here is f of x equal to 0 a constant polynomial, is the biggest question put forth to the students. The biggest question here is f of x equal to 0 a constant polynomial? Because 0 is a constant is the biggest question here, to be continued in the session. So the question put forth in the previous session is challenged to understand the difference between a constant polynomial and a 0 polynomial. So let's come back to the question, which is f of x equal to 0 a constant polynomial? Because 0 is a constant. So let's come back with the answer. F of x equal to 0 is called a 0 polynomial, but it is not called a constant polynomial. Let's see how we support the statement. It's called a 0 polynomial. That means anything you have in the right as 0 is called a 0 polynomial. And note, f of x equal to 0 is not a constant polynomial. The reason is very important out here. We don't call this as a constant polynomial because since degree of f of x equal to 0 is undefined. Except for non-zero terms, degree of a 0 term is undefined, is the biggest question out here. So for usually when I write in the form of 0, that means when I take f of x equal to 0, I can write this in various forms as 0 into 1. I can write this as 0 into 2 or 0 into k, or I can write this as 0 into x power 0. I can write this as 0 into x power n. So there is no fixed value for which I get this as 0, but 0 into any power of x also is 0. So I cannot decide exactly on what is that fixed value of x which I need to multiply to 0 such that I get 0. Therefore, it doesn't indirectly give me the exact understanding of whether the degree is 0 or n. Therefore, degree of f of x where equal to 0 is usually undefined. But some k where k is not equal to 0 is a constant polynomial, because when it is a non-zero term, it has a fixed value. Say for example, f of x equals 3 can be written as 3 times 1, which can only be uniquely written as x power 0 but cannot be expressed in any other form. Therefore, degree of this term is 0. Therefore, I call this as a constant polynomial. So, the difference out here is for a 0 polynomial, the degree is undefined, this being the case, and for a non-zero constant polynomial, the degree is 0, for which this is a constant polynomial because it can be written in a fixed factor, is how we differentiate. So, the learning outcome here is that for a non-zero constant polynomial, degree is 0, and for a 0 constant polynomial, degree is undefined, is how we understand the properties of differentiating between the constant polynomial and the 0 polynomial. So let's discuss the other type of polynomial called the monic polynomial. So let's see the definition of monic polynomial. A polynomial with leading coefficient equal to 1 is called a monic polynomial. So here the leading coefficient must be equal to 1 is what is the condition for a monic polynomial. That is, for example, p of x is equal to x squared minus 5x plus 6 has clearly its leading coefficient as an equals 1. If I take it as an x power n and x naught and etc. a naught plus a1x plus a2x squared, then an equal to 1 clearly gives me, or if I take a naught equal to 1, then clearly it is the coefficient of x squared, which is 1, gives me a naught equal to 1. Now, since the leading coefficient is 1, therefore this is a monic polynomial. Similarly, if I take q of x is 5 minus 2x plus x power 5 minus, now here I see that the leading coefficient here is minus 2, that implies a naught is minus 2, which is not equal to 1. Therefore, this is not a monic polynomial. So, we understand the monic polynomial through the leading coefficient being 1. Leading coefficient equal to 1 is a monic polynomial. Leading coefficient not equal to 1 is not a monic polynomial.